So here I've got some bromo alcohol, and I'm going to treat it with sodium hydride, NaH, in THF. I don't think we've seen sodium hydride yet. It is H minus, so it is a very strong base, right? What's the conjugate acid of sodium hydride? Conjugate acid of sodium hydride is just H2, gas, not an acid, right? Hydrogen gas is not acidic. So NaOH is a really good base. Surprisingly, it's a bad nucleophile. You'd think it'd be good because it's small and highly charged, but for a lot of reasons, including that it binds a little bit too tightly to sodium and is a little bit too repulsed by electron clouds. Turns out to be a pretty bad nucleophile. Anyways, sodium hydride, treating with this. So what will happen is that the OH will be deprotonated. How do I know I'm going to see deprotonation before, say, an E2 reaction? Well, remember, the E2 reaction has some pretty specific geometrical constraints that it needs to adopt before it reacts, but no geometrical constraints from taking a proton off an OH, though. So the first thing that will happen is it will deprotonate our OH, and so we'll get this alkoxide. All right, well, so now what? Well, let's take stock. We now have a very good nucleophile, O minus. We have a very good leaving group, bromine, in a very unhindered position, primary. And so this seems to be perfectly set up to do an intramolecular SN2. Check it out. So this is a cyclization. I'm making a ring. Intramolecular SN2. I know this strikes some students as crazy sometimes, but it's the least crazy thing in the world, right? Once I have a good nucleophile and a good leaving group in the pot, is a fait accompli, if you will. And notice that my ring size is also okay, right? Remember, 6-membered rings are kind of the most stable, but 5-membered rings turn out to be not only pretty stable, they're also faster from a kinetic sense because of orbital alignment. So this reaction to make a 5-membered ring like this is going to be very fast. Another one. Here's another bromo alcohol. I'm going to give it another base. This is potassium carbonate. It's not as strong of a base, but I don't need it to be completely deprotonated to start reacting. Essentially, sometimes this will take some of my acidic, this carbonate will take some of my acidic protons. After my base takes some of those acidic protons, I get this alkoxide. And now see how well this is set up to attack that, right? This is kind of like almost a kinetic product, right? It is just very easy for that bond to just pinch a little bit to give me a new 3-membered ring. Again, an SN2 reaction happens intramolecularly to give me a ring. And just like every other SN2, there are rules, right? It can't be too hindered. This is secondary, so it's fine. And SN2 reactions always give me 100% stereochemical inversion. And that's what I see here. So I'm starting with this S carbon here. You can kind of see what the transition state would look like here. And then I get only that enantiomer of the product. So it's stereo specific. I can only get one stereo isomer from this stereoisomer. Again, it's an SN2 reaction. So is that 3-membered ring stable? Surprisingly, yes. We said before, cyclopropanes are fine, and even 3-membered rings like this are formed very quickly. Will it do reactions later on? Sure. But if we're careful with it, that's a stable molecule. 3-membered rings with an oxygen like that are called epoxides. That's the old school name for it. The new IUPAC name is oxirane, and I've never heard someone use it unironically. So if epoxy sounds familiar, then that's where you've seen this from. So these things are reactive enough to be used in hard-setting epoxy coatings and glues and superglue and stuff like that. So it's a pretty important functional group. But again, it looks like it's be really unstable, but it is stable and pretty quickly made because these two groups are kind of stuck together, so they find each other pretty quickly to react. if we compare the rates of ring closing in this kind of reaction, we find that making 3-membered ring is the fastest along with 5-membered rings. So 3 and 5 are the best. 6-membered rings are a little bit slower than that. 4-membered rings are surprisingly slow. And then once you get to larger than 6, 7, 8, 9, the larger the ring, the slower the cyclization reaction is going to get. So how should we think about this? Well, like every other chemical reaction, you've got entropy and enthalpy to think about. So when I think of enthalpy, I think of ring strain, right? So ring strain is at its minimum with 6. It's pretty small in 5. But as you go sort of smaller than 5 and bigger than 6, ring strain gets bigger. Especially as you get to very large rings, ring strain gets very large. The other thing to consider is entropy. If I've got a very long chain, it's going to be entropically difficult for that OH minus to find that leaving group and get to be lined up. So it's very difficult to make big rings because it's hard to get them lined up. For a very small ring, 3 is kind of born lined up, right? It's almost hard to not be lined up to do this reaction. So there's a little bit less of an entropic cost. But the larger the chain gets, the more entropic cost you need to pay in. So again, the easiest rings to make are 3, 5, and 6. 4 and 7 are a little bit harder. And making large rings is pretty difficult. And that's a problem because a lot of good antibiotics are large rings, 10 to 15 rings. And so synthetic chemists have to work pretty hard to come up with good ways to make those big ringed antibiotics that we need. Here are 2 diastereomers that we're going to subject to the same conditions. Good non-nucleophilic base, sodium hydride in THF. So the first thing that happens, acid-base reaction. Acid-base reaction is way faster than any other kind of carbon-carbon-ish reaction that we're talking about. And so we get these anions, but again, we know a little bit about rings, and we know that those would be 2 possible geometries for those diastereomers. Again, we just talked about these reactions being SN2 reactions, but only one of these can actually do an intermolecular SN2 reaction. And that's the one where the nucleophile can get backside of the leaving group. Remember, that's always the geometry I need for an SN2 reaction. I always need to have my nucleophile be directly behind that leaving group on a line. For this one, I would need my nucleophile to come in from this direction. And there's no way I can kind of bend this thing so this oxygen is somehow coming in from that direction. It doesn't work. So there's not going to be any SN2 here. But here there will be, and the product is going to be another epoxide. Again, notice that I have inversion at the reaction center. This was a dashed line, now that carbon has a wedged line. So there's nothing special about this. It's an SN2 reaction. The only thing that's unique about it is that the nucleophile and the electrophile are part of the same molecule. I mentioned that epoxides are used in epoxy coatings, glues, stuff like that. So how does that work? This is why. So epoxides are easily formed, but they're also easily broken, which is no surprise for a 3-membered ring, right? There's a lot of ring strain going on here. And so just like we made it with an SN2 reaction, we're also going to open the ring with a different SN2 reaction. So now this is going to be our electrophile. Where's the leaving group? Well, think of the leaving group as the oxygen, where it's going to leave, but not like leave super far, right? Like maybe you're leaving your parents' house to go live on the garage for a while, right? You're kind of left, you're in the pool house, it's kind of your own space. Well, here oxygen isn't really going to leave, but we are going to break one of these carbon-oxygen bonds. And we can do that here because we'll be releasing that ring strain that we're building up. Right? So my nucleophile is my amine. Amines are good nucleophiles. This is going to be a good SN2 reaction. Which of these carbons do you think I should attack in an SN2 reaction? Well, what do I know about SN2 reactions? I know that it is sensitive to sterics, so I'm going to come at the less hindered end of the epoxide. So I'm going to come from the left. My nucleophile is going to tack backside to this oxygen. The oxygen is then going to leave, in scare quotes, right? It's not going to go too far, but I'm going to break that CO bond. So that is my ring opened product. Notice that the stereochemistry here didn't change because I didn't do anything to that stereocenter. And if I have an O- and an NH+, I'm probably going to get to this neutral amino alcohol pretty quickly. Okay, so this is a really important reaction in making drugs, in making plastics and polymers, and it comes from epoxide ring strain. So even though there's not a traditional leaving group here, and even though, if you look at this as an ether, we usually aren't able to just break up an ether like that. Here, ring strain makes it able to break that CO bond in some kind of SN2 reaction. Okay, so it's really nice for SN2 reactions as an electrophile. Attack it with some nucleophile. Nucleophile will attack from the less hindered end. You'll get a new bond like that. One more example. Before we made an epoxide on a ring, so let's use that in some new reaction now. So here is a ring epoxide. My cyanide is going to come in. Now, it's going to come to the less hindered side, so it's going to be coming to this side, not to that tertiary carbon here. But now stereochemistry is going to play a role here. Like I said, it's an SN2 reaction, and so I'm going to have 100% inversion at this carbon. What it looks like here is that my nucleophile is going to end up coming from behind my epoxide, so my stereochemistry is going to flip at that carbon. Right? The hydrogen that was there is now coming out, and the cyanide is going back. Okay? And then I break this bond. Because I'm not affecting this stereocenter persists in its configuration. So, epoxides. Easy to form if I can get to the SN2 reaction I need. Easy to break up with another SN2 reaction.